of our colleague and friend, Jeff Chapman. Jeff, a logistics and warehouse specialist, worked at ULA's warehouse here at Cape Canaveral. Jeff was a knowledgeable and dedicated coworker with a sharp memory and an amazing sense of humor. He was always willing to go out of his way to help others while going above and beyond in his own responsibilities. Jeff was a caring individual dedicated to his career, family, and friends, and will be missed by many.
OSM, LC, no one.
OSM.
Place SRB ignition SNA switch in the enable position.
SRB ignition enable. OSM.
Place SRB 2, verify CISA purge flowing GN2 to the CISA.
Verified.
OSM, verify the FCO, RCO, and OSM hold fire switches are in the proceed position.
Ready to proceed.
RCO and OSM switches are, and RLM, LC, no one. RLM. I'll keep step 140 open until the anomaly is resolved.
Roger.
We are going to extend the hold. There is an issue with the first stage that's being worked, and a new T0 will be announced when ready.
And for a team on net 1, this is LC. We're continuing to look at an anomaly. Team is off understanding that condition. We are extending the T-4 hold.
This is Atlas Mission Control at T-minus 4 minutes and holding. We are going to extend this hold for a little bit as we work an issue with the first stage, and we will have a new T0 for you when it's ready. As we remain in this hold, we are just taking another look at the weather. The probability of violating launch constraints is 10%. The ground winds are still 10 to 12 knots out of the west-southwest, and the temperature is 77 degrees Fahrenheit. So the weather is still within the launch commit criteria and looks favorable for our new T0. This is Atlas Mission Control at T-minus 4 minutes and holding. We're not hearing anything at the moment as the team is working the issue on the anomaly channel, but we are expecting to hear back from them soon as far as resolution and a new T0.
LC1, this is AC.
Go AC.
Ready to brief the RD-180 hydraulic issue.
Roger. LD net 1.
LD.
MD net 1.
MD.
Proceed AC.
Okay, we had a new sequence of the pressure setting, and we had to develop a troubleshooting plan to recover from that. That troubleshooting plan was implemented and successfully corrected the situation. RLM saw the event was necessary, and we are recommending proceeding.
LC concurs. LD.
LD concurs.
MD.
MD concurs.
RLM LC net 1.
This is RLM.
First step 140. Can you verify red line monitor and event table are in the correct configuration for terminal count?
Verified.
All right, team, stand by. Our anomaly has been corrected. We'll be coordinating a new T0. All personnel, stand by.
LC1, this is AC.
Go AC.
New issue, sir. We have from EGSC a data patching problem. Need to take that to 6.
Roger. Please convene the anomaly team. Provide a recommendation.
This is Atlas Mission Control at T-minus 4 minutes and holding. The issue with the first stage has been resolved. Another minor issue came up, a minor data issue, and the anomaly team has reconvened to work that. They're still working on a new T0 once that issue is resolved.
LCM1, as I say, right out brief, the Data patching issue.
Roger. LD Net 1.
LD.
MD Net 1.
MD.
Proceed, AC.
Okay, this was traced to a inadvertent patching issue in the ASOC data station. That has now been corrected. We are ready to proceed.
LC concurs. LD.
LD concurs.
MD.
MD concurs.
This is Atlas Mission Control at T-minus 4 minutes and holding. Sounds like the issue has been resolved. We have plenty of time remaining in our window this morning. We're just waiting for a new T0 now.
Roger. 10:13:000.
Good copy.
RC, please coordinate a new T0 of 10:13:000.
In work.
And ALC, please set up the clock for a new T0 of 10:13:000.
In work.
LCALC.
Go.
Countdown clock has been set for a new T0 of 10:13 Zulu.
Roger.
This is Atlas Mission Control at T-minus 4 minutes and holding. As you've heard, the issue has been resolved and we have coordinated a new T0 of 6:13 a.m. Eastern Time.
LCRC1.
Go, RC.
New T010:13:00, approved by the range.
Roger. And with that, all steps are complete prior to status check. LC switch to the ready position. All personnel stand by for status check at L-minus 7 minutes.
We remain in the planned built-in hold as we continue to prepare for liftoff. The hold was extended just a little bit to solve a couple of anomalies, but we have a new T0 of 6:13 a.m. Eastern Time. In a few moments, launch conductor Scott Barney will poll the launch team for the final go to pick up the countdown. 29 engineers and managers are polled for system status and readiness to proceed. This is the final status check before launch for all Atlas vehicle systems, ground systems, the spacecraft, and the U.S. Air Force Eastern Range. The vehicle system readiness poll includes electrical systems, hydraulics, pneumatics, propulsion systems, flight control, and propellants. Let's listen in as Scott Barney performs the final polling of the launch team.
Status check to proceed with terminal count. Atlas systems, propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur systems, propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
HASGAS.
Go.
Electrical systems, airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
GCQ.
Go.
Operations support.
Go.
COM.
Go.
Umbilicals.
Go.
ECS.
Go.
Redline monitor.
Go.
Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
Go.
Anomaly chief.
Go.
RC.
Clear to proceed.
Launch director.
Launch vehicle is ready to launch.
Mission director.
This is the mission director. You have permission to launch.
Proceeding with the count. ALC verified T0 is set for 10:13 Zulu.
Verified.
Polling is complete and the launch team has given the go for launch. From T-minus 4 minutes until liftoff, you will be listening to launch conductor Scott Barney and his team performing the final steps in the countdown procedure. You will hear the team call out that Atlas LO2 topping has been secured, followed about a minute later by the call out for transferring the Atlas and Centaur stages from ground facility power to internal battery power. At T-minus 1 minute 55 seconds, the team will command the launch sequencer to start, followed shortly by securing the Centaur LH2 and LO2 topping activity. At T-minus 1 minute 40 seconds, the team will command the flight control system to launch enable and arm the flight termination system. In the final minute, the Atlas tanks will be verified at flight pressures, followed by verification of Centaur tank pressures. A final status check of Atlas, Centaur, and AEHF 5 readiness is conducted at T-minus 25 seconds. At T-minus 3 seconds, the RD-180 engine will roar to life. After liftoff, you'll hear the voice of Patrick Moore providing launch vehicle ascent data. This is Atlas Mission Control at T-minus 4 minutes and holding. We anticipate releasing the hold in just a few moments.
T-minus 4 minutes and counting. 3, 2, 1, mark. 3:55.
Ground pyros enabled.
The countdown clock has resumed and we are go for launch at 6:13 a.m. Eastern.
T-minus 3 minutes.
Securing LO2 topping.
Atlas tanks to flight pressure.
2 minutes, 50 seconds.
ATS internal.
$159,
Vehicle internal.
$155,
Launch sequencer start.
$150,
Securing Centaur LH2.
Securing Centaur LO2.
$140,
Launch enable.
$137,
FTS armed.
T-minus 90 seconds. The launch vehicle, payload, ground systems, and eastern range are go for launch.
120,
OCU's armed. Count started.
115,
Reduce ECS for launch.
Roger.
110,
Vent valves locked.
T-minus 1 minute.
Rock, report range status.
Range green.
T-minus 40 seconds.
Stable at step 3.
$28 seconds.
ECS reduced for launch.
Roger.
25,
Status check.
Go Atlas. Go Centaur.
Go AEHF 5.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2. We have ignition, and we have liftoff of the United Launch Alliance Atlas V rocket with AEHF 5 for the United States Air Force Space and Missile Systems Center.
Now 10 seconds in. Vehicle throttling down to 67% thrust. Engine response looks good. And PU system has gone to closed loop control as expected. System response looks good. 25 seconds in. RG-180 engine operating parameters look good. Now 35 seconds. Mach 1 Atlas V is now supersonic. Now 45 seconds in. RG-180 continuing to look good. Now passing through max Q. And engine throttling back up to 94% thrust. RG-180 engine operating parameters look good. Seeing good chamber pressure on all 5 SRBs. Good symmetric burn. Just passing 1 minute now into flight. RG-180 continuing to look good. Also seeing good chamber pressure across all 5 SRBs. Engine now throttling down to 75% thrust as expected. Engine response looks good. Standing by for SRB burnout shortly. And we're seeing burnout on all 5 SRBs. Engine back up to full thrust. Standing by for SRB jettison. And we have good indication of jettison of all 5 solid rocket boosters. 1 minute, 50 seconds into flight. Vehicle's gone to closed loop guidance. Now passing 2 minutes into flight. Atlas V is now 38 miles in altitude,
48 miles downrange distance, traveling at 4,700 miles per hour. 2 minutes, 15 seconds into flight. RD-180 engine operating parameters continue to look good at full thrust. Vehicle body rates looking good. Just under 2 minutes now remaining in the boost phase of flight. Engine now throttling to maintain 2.5 G acceleration limit. Engine response and vehicle body rate response looks good. RCS pyro valve has been fired. Reaction control system is pressurizing to flight levels. Now coming up on 3 minutes into flight. RD-180 pump speeds and injector pressures continue to look good as it's maintaining that throttle limiting. 3 minutes, 10 seconds in. Vehicle body rates continue to look good. Standing by for payload fairing jettison. And we have good indication of payload fairing jettison. And CFLR jettison complete as well. Vehicle now throttling back up to 95% thrust. Engine response looks good. 3 minutes, 40 seconds in. And engine is now throttling to maintain 4.6 G acceleration limit. Engine response looks good. Now passing 4 minutes into flight, Centaur's begun the boost phase chill down sequence. RD-180 engine continues to look good as it maintains that 4.6 G throttle acceleration limit. 4 minutes, 15 seconds in, standing by for BECO shortly. And we have BECO booster engine cutoff standing by for stage step. And we have good indication of Atlas Centaur separation. We have pre-start on the RL-10, standing by for ignition. We have ignition and full thrust on the RL-10. Chamber pressure looks good, body rates look good. This first burn of today's mission will last approximately 7 minutes. Now at 5 minutes into flight, the Centaur is 110 miles in altitude, 500 miles downrange distance, traveling at 13,900 miles per hour. RL-10 chamber pressure continues to look good. Vehicle body rates also maintaining good values. 5 minutes, 20 seconds into flight.
This is Atlas Mission Control at T plus 5 minutes, 30 seconds. Patrick Moore just confirmed the successful completion of the early phase of today's flight, and all systems continue to operate nominally. The mission is currently in the first of 3 Centaur engine burns. Our next event, Centaur main engine cutoff, will occur in approximately 7 minutes. I'm joined now by Lieutenant Corey Williams of the U.S. Air Force's Space and Missile Systems Center. Lieutenant, thank you so much for joining us today.
Glad to be here, Amanda.
So we've just seen a great liftoff of the 5th satellite in the AEHF constellation. What was it like to watch that liftoff?
It feels great. This launch was a major milestone for the Air Force and a big win for the United States and its international partners. So on behalf of SMC 2.0, I would like to thank our industry partners, Lockheed Martin, Northrop Grumman, and United Launch Alliance.
Can you talk a little bit more about the international partners?
Certainly. So currently we have 3 international partners on our program: Canada, the Netherlands, and United Kingdom. And we are also in the process of negotiation with Australia's Department of Defense to bring them on as a 4th partner as well. So in line with guidance from our Secretary of Defense, the Air Force is actively pursuing partnerships with our allies around the world. This improves interoperability and makes us a more lethal combined fighting force.
Sounds like you guys have a lot of great plans for the future. So before liftoff, I touched a little bit on the capabilities of today's satellite. What is AEHF's mission?
So Once integrated, the satellite will join the AEHF constellation with the primary mission to provide survivable, global, secure, protected, and anti-jam communications for high-priority military ground, sea, and air assets. Additionally, the AEHF constellation also allows the President of the United States and combatant commanders to control their strategic and tactical forces through all phases of conflict, through all phases of war.
So what is the coverage of the constellation?
So the AEHF 5 completes a full constellation of 5 interconnected satellites providing continuous worldwide 24-hour coverage between 65 degrees north and 65 degrees south latitude. Not to mention, the United States Air Force procured an additional satellite, AEHF 6, which will be added to the constellation in the near future.
So there's another satellite on the way. When is that launch planned?
The projected launch for AEHF 6 is March 2020, so not too long until we get to come back for yet an exciting lift.
Well, great. Can't wait for that. Now that we've seen the successful liftoff of the AEHF 5, how will that get integrated into the constellation?
So the satellite will initially be put into a geosynchronous test orbit in view of our CONUS-based ground assessment facilities to perform checkout, on-orbit tests, and antenna calibrations. Upon completion of these activities, it will then be turned over to operations.
So now that we've talked a little bit about the satellite and its capabilities, what is your role in all of this?
Sure. So I'm a program manager with just over 3 years of active duty service. I've worked on the AEHF program for all of my career so far, and my current role in the program is I'm responsible for the production operations.
Awesome. Well, that sounds like cool work to do. Thank you so much for talking to us about AEHF. You must be really proud to be a part of all of this.
Absolutely. And the Air Force is proud to be part of this history and heritage, thanks to the great work and partnership between the U.S. Air Force and its industry partners.
Well, thanks so much for talking to us. We'll now return to the flight as we approach main engine cutoff 1. Let's listen in.
Now passing 9 minutes, 30 seconds into flight. And about 2 minutes now remaining in the burn. Centaur systems continue to perform nominally throughout this burn, continuing to see good performance on the RL-10 main engine, as well as periodic thruster firings, and Centaur is maintaining very stable body rates. Now at 10 minutes, 30 seconds into flight, Centaur is 144 miles in altitude, 1,900 miles downrange distance, traveling at 16,780 miles per hour. Less than 1 minute now remaining in the burn. Centaur PU system has maintained a request for a LOX-rich burn throughout this first burn, not uncommon. Centaur RL-10 engine operating parameters continue to look good throughout this burn. Now 20 seconds remaining until MECO. And standing by for MECO shortly. And we have MECO. Body rates have damped out nice.
This is Atlas Mission Control at T plus 11 minutes, 49 seconds. Patrick Moore just confirmed the first Centaur main engine cutoff. Our next event, main engine burn 2, will occur in approximately 10 minutes.
Coming up yet. Now passing 12 minutes into flight.
ULA's next Atlas launch is the Orbital Flight Test. The emergency detection system is unique technology developed for the Atlas V Starliner and is designed to protect the crew and monitor the health of the rocket. Let's learn more.
We're sitting in the Systems Integration Lab at the Centennial Campus at United Launch Alliance. My name is Stefania Mooring. I am the Human Spaceflight Integration Lead.
And my name is Matej Niderčić. I'm a Guidance, Navigation, and Control Engineer, and we're going to be talking about the Emergency Detection System today. So the Atlas V is a phenomenally reliable vehicle, and that's one of the reasons why Boeing chose the Atlas to launch their Starliner capsule and to launch astronauts to the space station. Part of the thing about human spaceflight is that you need an extra layer of protection. You want to keep those astronauts safe. And so, in addition to the reliability of the Atlas V, we wanted to add a system that can detect if something is going wrong with the rocket. So we added this EDS system, and we started developing it about 9 years ago in the early days of the Commercial Crew Program. We started coming up with concepts of what does it mean to create an emergency detection system? What are the sort of things we need to monitor on the rocket to ensure that we're keeping that crew safe in all conditions? One of the great things about the hardware that we're using for this is that it's the same sort of hardware that we've been flying for years on the Atlas V with just some modifications.
So there is this magic line of how you set your abort triggers in terms of what can we recover from versus when do we know this is going to be a time when we need to ask the crew to go for an abort.
We can detect if we need to abort faster than you can blink an eye, which is a lot faster than any human can ever react. And what we want to do is ensure that we're keeping the crew safe by making sure that those lines are where they need to be. Having to fine-tune that for the different parts of flight, whether we're on the booster or whether we're on Centaur, whether we're coasting in preparation for separation, all of that was a very carefully thought out process to make sure that we're still keeping the crew safe at all times, and that line isn't too close or too far away.
So the EDS is also there to provide some of the phases to the spacecraft. So it's not just there for the abort system itself. So as part of nominal flight, the EDS is telling the spacecraft where we are in flight, so that way the spacecraft can also do critical operations like jettison of the ascent cover in flight, or knowing when they need to separate the spacecraft once we're completed with Centaur phase of flight. In our industry, you'll hear us use the term failure tolerance. And so what that means is that I actually have a full backup system in case the primary doesn't work anymore. For example, if I lock my keys in the house and I have a separate set of keys in a hide key location, I now have that extra set of keys to get in the house. In terms of the EDS itself, if you look back behind me, we've got 2 boxes. So if one box were to fail, we still have that backup box to not only do the health monitoring and the boards, but also for providing the critical flight phases to the spacecraft for their operations.
Yeah, and that redundancy applies to every part of the rocket. That's one of the critical lessons that we've learned over the years, is that it's important to have redundancy and failure tolerance in all the critical aspects of the rocket.
We actually test it here in our SIL once we receive it from our supplier. And we run that through what we call a test like you fly configuration. So we actually fly the boxes as if you were flying on a real rocket before we ship them out to the Cape to get installed on the vehicle.
We want to make sure that we're flying with hardware that is in the same configuration that we're going to have on launch day. We want to make sure the connectors are the same. We want to make sure the boxes are the same distance apart. One of the things that we do here is simulate the trajectory thousands upon thousands of times to make sure that under all the conditions we expect to see in flight, the software holds up and the hardware works together.
So for OFT, EDS will actually be flying on that vehicle in what we call passive mode. So what that means is the EDS will still be doing all of the monitoring functions, but it will not be declaring any aborts. This provides us with critical data post-flight, so that way we can determine if there's any fine-tuning that we need to do with those thresholds.
It's been a lot of effort by a lot of people to make sure that we're going to be keeping our astronauts safe.
Everyone at ULA is very excited to be launching the Starliner mission.
We recently had the pleasure of hearing from astronaut Chris Ferguson, who will be riding atop an Atlas V in our crewed flight test following the launch of OFT. Let's hear what he had to say about these upcoming launches.
Hi, I'm Chris Ferguson, Boeing astronaut. I just want to wish United Launch Alliance safe and successful journey for AEHF, the 80th launch of the Atlas V series. Pretty exciting for them. Pretty exciting, of course, for us at Boeing, because the next one out of the chute will be OFT, the orbital flight test of the Starliner vehicle, which you see over my left-hand shoulder here, to the International Space Station. Followed shortly thereafter by a crew of 3, myself and 2 NASA astronauts, Nicole Mann and Mike Fink. Pretty special time, pretty neat in history. The Atlas series of rockets has changed very much over the years. The last human to launch aboard an Atlas was Gordon Cooper back in the 60s. Pretty excited to be following in big footsteps like that. So again, best of luck to United Launch Alliance on the launch of AEHF.
So we have some really exciting missions coming up. I can say that I'm really looking forward to ULA's part in launching U.S. astronauts from U.S. soil on an Atlas V rocket so soon. For my fellow Atlas fans, you may have noticed that over the last week, we've asked the social media community to share photos of the Atlas V 551, the same configuration that just launched AEHF, using the ULA Anywhere app. So let's take a look at some of our favorite submissions. As I mentioned earlier, AEHF 5 production began in ULA's Decatur, Alabama production facility. ULA Vice President of Production Operations and Supply Chain, Cindy Nafis, joined us recently to give some insight into the Atlas production process.
We are in ULA's Decatur, Alabama production facilities where we build our Atlas V rockets. We're currently sitting in our final assembly area, and this is the end. Where we start is we start from raw material in our skin, ring, and dome chem processing area. And we actually have 3 major, I'm going to say, functions in our build process where we do our machining. Then we move on to our major assemblies where we do welding and bolting things together. And then we move into final assembly where we put everything together, our tanks, and we send it off to be tested in our pressure test facility. And then we load it on the Mariner and it heads to either Cape Canaveral or Vandenberg Air Force Base for its launch. So we have a lot of processes involved in building our Atlas V rockets, you know, from machining to chemical processing, you know, so there's a lot of different processing with a lot of different skills, and our technicians are highly trained and certified to do this work. In addition to that booster, the Atlas V booster behind me, we also produce and build in this factory the Centaur second stage, which is a stainless steel design. It is the highest performing second stage in rocket production today. And we assemble that with the Centaur forwarded adapter into the final assembly area, which is currently in our clean room. And then it also is loaded onto the Mariner and shipped to the launch site. So we're hearing a lot of noise, and that's because there's a lot of work going on the other side of this wall right behind me. and that is where we're installing 9 new weld stations for our Centaur 5 production. That will be our new second stage that will be on top of our Vulcan Centaur rocket that is currently in production in the factory.
We are now approaching main engine start 2. Let's listen in.
And we have pre-start. We have ignition and full thrust. Chamber pressure looks good. Body rate stamping out nicely. Now passing 23 minutes into flight. And PU's gone to closed loop control.
This is Atlas Mission Control at T plus 23 minutes and 16 seconds. We just heard confirmation of the second main engine start. Main engine cutoff 2 is planned to occur in approximately 6 minutes.
Now passing 23 minutes, 30 seconds into flight.
Recently, we had the opportunity to hear from AEHF 5 trajectory engineer Tyler Strickland about the flight path that today's satellite is currently on. Let's hear what he had to say.
Hi, I'm Tyler Strickland. I'm the mission engineer for flight design, and I worked on the trajectory for the AEHF 5 mission. You may recognize me from some of the launch commentary I've done in the past as well. I'm here today to talk to you about some of the different aspects you'll see during today's flight. For AEHF 5, we've added an extended mission kit. Now, what the extended mission kit does is allow us to coast for a longer amount of time, about 5 hours on today's flight. Now, the reason we do the extended coast is to get us further out all the way to apogee. This is also referred to as a Hohmann transfer and is one of the most basic flight design components that we try to utilize. The Hohmann transfer is one of our standard toolkit kind of items when you're talking about trajectory design or flight design. What that is we go to a park orbit, which will be circular. Then we coast and perform our second burn, which puts us in a geostationary transfer orbit, which looks like an ellipse. When we coast out to the end of the ellipse, or at apogee, the furthest point from Earth, that is the most efficient place to put a burn, which will raise our perigee the most. That's a main difference you'll see between AEHF 5 and the most recent mission for this program, AEHF 4. Because of the extra 2 hours, we were able to reach apogee and raise that perigee a lot further than we did previously. As I mentioned earlier, it's the addition of the extended mission kit that allows us to have this extended coast of over 5 hours. What the extended mission kit does is increase our battery capacity on the Centaur. If you're going to coast for longer, you're going to need more power. We also add additional insulation for the Centaur so that we can protect it from the harsh space environment and have better propellant characterization and better understand and protect those liquid propellants over such a long period of time. Another fun fact about this mission is that we're using minimum residual shutdown for the third and final Centaur burn. What that means is that we're actually using every single bit of performance we have on the vehicle. Rather than using guidance commanded shutdown, where we actually target an orbit and stop when we get there, we're going to use everything left on the vehicle, all the remaining propellant, so that the customer gets as much energy as we can give them. So the combination of the extended mission kit and minimum residual shutdown means we're working with a much more efficient and optimized trajectory, which is getting us a lot closer to geosynchronous orbit, which is ultimately the goal for this mission.
Today's liftoff marks the 80th for an Atlas V rocket. Since its inaugural flight in 2002, ULA's Atlas V has safely, reliably, and accurately launched vital national security, science and exploration, and commercial missions. Launching from California's Vandenberg Air Force Base and Florida's Cape Canaveral Air Force Station, the list of launch accomplishments for this amazing rocket and team is long and impressive. Atlas V missions have helped save lives by orbiting more than 40 national security payloads, including the Air Force's AEHF, GPS, MUOS, SBIRS, and WGS satellites. Missions to the Moon, Jupiter, Pluto, and multiple trips to Mars, all launched on Atlas V rockets, have expanded our understanding of the universe. And our world is more connected with state-of-the-art communications and imaging satellites delivered to orbit by Atlas V rockets. As we look ahead, Atlas V will continue its legacy of changing the world one launch at a time when it returns astronauts to space from U.S. soil aboard Boeing's Starliner spacecraft. We're now approaching main engine cutoff 2, which will be followed by separation of today's aft bulkhead payload, TDO, 31 seconds later. Let's return to the flight.
Approximately 30 seconds now remaining until MECO 2. RL-10 chamber pressure continues to look good, and we will be standing by for MECO 2 in approximately 10 seconds. And we have MECO standing by now for TDO separation. And we have good indication of separation of the TDO spacecraft. Centaur is now entering a 5-hour coast period prior to ignition for the third burn.
I'd like to thank Patrick Moore for his support of today's show. For continuing updates on the progress of today's mission through this 5-hour coast, the final Centaur burn, and through spacecraft separation, you can follow ULA's live launch updates blog at ulalaunch.com or join the conversation on Twitter and Facebook. We'll complete our live coverage with another look at today's liftoff, which occurred at 6:13 a.m. Eastern Time. I'm Amanda Sterling, and on behalf of the entire launch team, thank you for joining us and have a great day. Ignition, and we have liftoff of the United Launch Alliance Atlas V rocket with AEHF-5 for the United States Air Force Space and Missile Systems Center.
Now 10 seconds in. Vehicle throttling down to 67% thrust. Engine response looks good. And PU system has gone to closed loop control as expected. System response looks good. 25 seconds in.